Hi! As we all know, the angle of elevation of celestial objects above the horizon tends to change rather predictably with distance to the object's GP, geographical position. When we are at the GP, the object is in the zenith, 90 degrees above horizontal, and as our distance from the GP grows, the angle decreases. But it doesn't just decrease, it decreases at a constant rate of 1 degree per 60 nautical miles, or 69 statute miles or 111 kilometers. Now this is a bit problematic for flat earthers because no matter which way you look at it, this doesn't fit a flat plane. On a flat plane, if the height of the object above the plane is h, and the distance from the GP is z, the elevation angle would be equal to alpha, which is equal to inverse tangent of h over z. We can calculate how fast this should change with changes in z. So the derivative of alpha with respect to z is this, which depends on z. This means that even if we calculate h so that this equals 1 degree per 60 nautical miles at some z, the value will be different at different z, so a flat shape is out of the question. But does it mean the shape has to be spherical? Can we figure out what the shape would have to be for this constant change of angle to hold at different distances from the GP? Yes, if we use the appropriate tool for the job, math. Let's do so then. Let's first reduce the problem to 2 dimensions. Since the angle decreases the same in all directions from the GP, the problem has rotational symmetry, and so we can just consider a single direction. So instead of calculating the shape of the whole surface, we can just calculate the shape of its intersection with a plane containing the object and its GP. Within that plane, we will introduce regular Cartesian coordinates, x and y. We'll say that the celestial object is at the origin, 0, 0, and the GP is at 0 minus h. H will be the altitude of the object above our surface, and we will leave it unspecified for now, it's just some constant number. Now the shape of our surface will be described by some function y of x, and it is this function that we want to calculate. Turns out we already know 2 things about it. First, that y of 0 is equal to minus h. This is just the requirement that the celestial object is at altitude h. And the second is that the derivative of y at 0 is 0. This condition stems from the requirement that the object is 90 degrees above horizontal at the GP. The horizontal is the tangent to the surface, and at the GP, so at x equal to 0, it has to be perpendicular to the direction to the object, so it has to be parallel to the x-axis. The tangent of the angle between the tangent to the graph and the x-axis is equal to the derivative of the function, so the derivative has to be tangent of 0, which is equal to 0. But that is not enough, we need more. So let's consider some point on the graph, at coordinates x and y of x. The horizontal, which is the tangent to the surface at that point, will be at some angle beta to the x-axis, with the tangent of that angle being the derivative of y at x. Now, the angle from the x-axis to the celestial object is gamma, with tangent of gamma equal to minus y over x. So the elevation angle of the celestial object is alpha, which is the sum of beta and gamma, which is equal to this. Now what we're interested in is the rate of change of this angle. So it's tempting to just calculate d alpha over dx, but this is not the rate of change that concerns us. What we need is d alpha over dz, the rate of change with respect to the distance along the surface, but that can be calculated as the ratio of d alpha over dx to dz over dx. Now dz over dx is simple to calculate. If we move by dx along the x-axis, we have to move by dy in the y-axis to stay on the surface, with dy equal to derivative of y times dx. So dz squared is equal to this. Thus dz over dx can be expressed like this. We can also calculate d alpha over dx, and it's equal to this expression. So if we then divide by dz over dx, we get d alpha over dz, which is this. And now this is what is supposed to be constant, 1 degree over 60 nautical miles. So let's label this rate with c. and we can rearrange all of this to extract the second derivative of y. And this is our final equation. This is an ordinary differential equation of the second order, and the solution to that equation with the initial conditions y of 0 equals to minus h, and the derivative of y at 0 equals to 0 is the shape of the surface. Now this equation is what would professionally be called awful. Solving it analytically would be a daunting task, so we'll make it easier for ourselves and we'll solve it numerically. I won't go into details here, but I've written a simple solver using the RK4 integration method and plotted the results using nuplot. I'll link to the solver in the description. Now, what shouldn't be surprising, the resulting shape depends on the height we chose for the celestial object, the h in the initial condition. I've prepared an animation with h varying from 1000 nautical miles to 30,000 nautical miles, but before I show it to you, let's look at the shape for the altitude commonly assumed by flat earthers for Polaris, 2700 nautical miles. Here we can see that the surface is pretty weird, but if we look closely, it does follow the rule of uniformly decreasing angle. Here, somewhere in the middle, the angle is 45 degrees, and as we get to the end, which is 5400 nautical miles along the surface, the angle approaches 0. Let's now look at the animation. Note that the surface is always drawn to a length of 5400 nautical miles, as beyond that distance the elevation of the object should become negative, and the equation isn't guaranteed to work. So here goes. As we can see, the surface satisfying the condition of angle decreasing at a constant 1 degree per 60 nautical miles is never flat. It is even concave close to the GP for lower altitudes of the celestial object. But the greater the altitude, the more the shape starts resembling a quarter of a circle, which would correspond to a hemisphere in 3 dimensions if we rotated that around the y-axis. In fact, let's get back to the differential equation for a bit. Let's substitute t equals to y plus h here. This will make t of 0 equal to 0 and the celestial object be at 0h. Then y equals to t minus h, derivative of y is the derivative of t, and the second derivative of y is the second derivative of t. And the equation takes the form. Now, if we go to the limit of h tending to infinity, this will correspond to a star being infinitely far. We see that h is only in this part of the equation, with numerator being linear in h and denominator being quadratic, so when h is infinite this whole part becomes 0 and the equation becomes. This can be solved analytically, and the solution is a circle. This proves that the shape indeed approaches a circle as the star gets further and further away. I'll leave the full calculation as an exercise to those watching though. Now consider that pretty much every point on the surface of the Earth is the GP of some object in the sky. And every such object follows the same pattern, 1 degree lower per 60 nautical miles from the GP. So the surface of the Earth has to resemble one of these shapes when any point is the GP. So, for example, the ones for lower altitudes won't do. If we say that this is drawn for object A, and object B's GP is somewhere here, then if we copy the surface's shape and try to fit it at B's GP, it should overlap with the original one. But it doesn't. This just doesn't work. The only shape among these with the correct symmetry, such that it looks the same from all points, is a sphere. If we try the same thing, mark A's GP and B's GP, and then copy the shape and try to fit it at B's GP, it fits pretty well. So this is actually very strong evidence that the surface of the Earth is, in fact, a sphere. Thanks for watching and see you in the next one.